Welcome back to The Explainer. Today we're jumping right into episode 1.4, Subsea Surveying, Positioning, and Foundations. Basically, we're talking about millimetric seabed precision. I'm absolutely thrilled to get into this one because we are looking at what is literally one of the most incredible feats of modern engineering. We're talking about pinpoint accuracy in environments that are actively trying to crush and push away everything we build. Just imagine this operational scenario for a second. How do you park a multi-ton steel cylinder on a seabed that you can't even see? You're operating in currents you can't fight. You're deploying from a vessel that's bobbing around with every single surface wave, and yet you need to land this massive object within centimeters of a target. Well, that's just a routine Tuesday in subsea foundation installation. And it really only works because of two things: positioning systems that never ever lose track of where you are, and a foundation design that literally turns the ocean's suction into holding strength. And to give you a sense of the sheer scale of the hardware we're dealing with here, 30 meters. Suction piles for major subsea structures, they aren't just little stakes in the ground. They can be 15 to 20 meters across, and they penetrate up to 30 meters deep into the seabed. To put that into perspective, that is basically a 10-story building buried directly into the ocean floor. So you might be wondering, why go to such extreme lengths? Well, oil and gas still supply roughly 80% of world energy demand. But since about 1995, those easy-to-reach shallow reserves have been heavily depleted. So the industry has been forced out into these extreme deep water environments. We literally have to build on this unknown deep seabed that is completely unlike a stable onshore construction site. It has to be rigorously surveyed field by field just to ensure every structure's weight-bearing capacity is engineered for that highly specific soil. Okay, let's dive into this. How do we actually find our exact spot on the seafloor? As we all know, standard GPS signals do not travel underwater, right? So to position these massive structures, we rely entirely on acoustics, sound waves. But here's the catch. The speed of sound underwater isn't constant. It fluctuates based on the temperature, the salinity, and the density of the water column. And because these properties change randomly and periodically, our acoustic positioning systems require constant, ongoing calibration using specialized probes, just to maintain that accuracy. Which brings us to our two primary underwater positioning strategies, LBL and USBL. LBL, or long baseline, uses an array of transponders pre-deployed directly onto the seabed. It provides incredibly high local precision by triangulating a target, and the best part is it operates completely independent of water depth. USBL, on the other hand, ultra-short baseline, uses a single transceiver mounted right on the hull of the vessel. It measures phase angles to a subsea transponder. USBL is fantastic when you need to track a moving object, say a remote-operated vehicle or a load on a crane wire, across a wide area without having to go through the whole hassle of laying down a seabed array beforehand. But there's a pretty crucial physical warning here. Because USBL relies on calculating angles across a very short baseline on the ship's hull, any tiny angular error translates into a growing positional error the further away the target is. By the time you reach ultra-deep water, that tiny angle error, it means your payload could be way off target. That is exactly why, for ultra-deep water precision work where margins are practically zero, the pre-deployed LBL seabed array is the much, much more reliable choice. So now that we know how to find our coordinates, how do we actually anchor a structure there? I absolutely love this quote from our sources. A suction pile is like a syringe plunged into wet sand. It's brilliant. It takes these super complex soil mechanics and makes them something we can instantly visualize. You push a syringe in partway under its own weight, right? Then you pull back on the plunger, and the resulting suction drags it the rest of the way down. That syringe concept translates into a really fascinating 4-act installation sequence out in the field. Act 1 is overboarding, carefully lowering the pile through that dynamic, wave-battered splash zone. Act 2 is self-weight penetration, where gravity takes over and the pile sinks passively until the soil resistance matches its submerged weight. Then, Act 3 is venting. This is opening valves on the top cap to let trapped water escape so you don't accidentally create a pressure lock. And finally, Act 4 is pump out. Sub-Sea ROVs attach to the pile and pump water out of the sealed top, creating an internal underpressure, a vacuum, that drives the pile down to its final design depth. Now, that sealed top cap creates the real magic of a suction pile, reverse end bearing, or REB. This isn't just some nice-to-have design bonus. It is the entire reason these piles can withstand hurricane-level storm loads without being physically massive. By keeping that top cap perfectly sealed once it's installed, any vertical pull on the pile creates a massive vacuum force that resists the uplift. It's exactly like trying to pull a fully sealed plunger straight up out of a bucket of water. Depending on what the ocean throws at it, the foundation uses different physical forces to survive. So for long-term, slow creep loads, like a steady ocean current pushing against a moored structure over months, the foundation relies primarily on the external skin friction of the soil against the steel. But when peak storm loading hits, a sudden, violent, massive pull upward, reverse end bearing is the ultimate primary defense holding that structure firmly to the seabed. Honestly, without REB, you'd need a vastly heavier and longer pile just to get that same hold from skin friction alone. Now, I want to challenge you for a second. Put yourself in the shoes of the installation engineer sitting in the control room on the vessel. You can't just tell the ROV to turn the pump on and wait. You are actively monitoring real-time pressure and depth gauges. So what is the one specific trend during the pump-out phase that tells you this foundation is failing right there in the moment, before the installation is even finished?
The answer? Internal plug heave. If you see the embedment pressure rising, but the penetration depth stops changing, and instead the soil plug inside the pile starts lifting upwards, well, you have a massive problem. It means your suction differential isn't driving the heavy steel cylinder down into the soil anymore. Instead, the suction is literally ripping the soil structure apart and sucking the seabed right up into the pile.
If you see that plug heaves trend, the immediate action is clear. You must stop or dramatically reduce the pump rate immediately. And why does this matter so much? Well, if you ignore it and keep pumping, the pile might actually eventually reach its target depth. It'll look perfectly installed from the outside. But inside, you have completely destroyed the integrity of the soil plug. You've compromised the reverse end bearing capacity, meaning the very first time a major storm hits, that foundation, which remember you are relying on for the entire life of the field, is absolutely going to fail. So we've seen how to accurately position these massive structures and how they grip the seabed with such incredible strength. But there is a glaring physical limitation we haven't even talked about yet: getting it down there in the first place. I'll leave you with this provocative thought. How exactly do you lower a 170-ton piece of hardware to a depth of 3,000 meters, when at that depth, the massive 5-inch steel wire rope holding it up weighs 170 tons on its own? At 3,000 meters, the wire's safe working load is entirely used up just holding itself. That physics problem dictates absolutely everything about vessel selection and deep water lifting, and it's exactly what we're going to unpack in our next explainer. See you then.